when you pass a tensor into a neural network, it typically has to be in a certain shape, and then the output tensor that comes out of a neural network, so in other words, the patterns a neural network has learned, the tensor again has to be in a certain shape. So it's good to be able to deduce different elements of a tensor by its shape. So if we wanted rank 4 tensor, let's get its 0th element. What does that look like? Which is this 3 tensor here. So see how we've indexed onto this second shape here? Now the shape changes because we're getting this set of 3 here, this set of 3 tensors. And so the shape here is 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Again, it'll take quite a bit of practice to get used to that, but that's just a brief overview. Now, what we might do is get all of the shape, the rank, axis or dimension, and the size of our tensor. So we just saw the 0th axis. Let's go rank for tensor dot shape. You might be able to guess what this is already. Rank for tensor dot ndim, so the number of dimensions. And then let's get the size of our tensor. Before I even type any of these, you might be able to deduce what they actually are already. So what's the shape? Probably going to be similar to what we set the shape as. The ndim, remember that's the number of dimensions in our tensor. And the size is what, if we come back to our keynote? The size is the total number of items in the tensor. Out of all of these, I think size will probably be the one you use least often, but I'm just putting it here for completeness. So if we go there, boom. So we look, these come in order again. So the shape is 2, 3, 4, 5, yep. The number of dimensions is 4, that makes sense because it's 1, 2, 3, 4, beautiful. And then the size is there's 120 elements. Now, what might that be? I'll give you a hint. 2 times 3 times 4 times 5. What do you think this is going to equal? 120. Beautiful. Okay. How about we print out some various attributes of our tensor, make them a bit more readable. So I want to show you, get various attributes of our tensor. This is what I often do to sort of create I call this pretty print statements. I mean, there is a function called pretty print, but when I'm trying to figure out or visualize my tensor data, I typically set up a bunch of print statements like this, especially when I'm inspecting the outputs of a neural network. So print, so I want to get the data type of every element. Boom, that's what I want. And then I want to get the number of dimensions, which can be the rank. And again, typing this stuff out is tedious when you first do it, but it does help visualize. I mean, we could put this into a function if we wanted to later on. Print, and now how about the shape of our tensor? That's going to be rank for tensor.shape. I'm not sure why that disappeared. Beautiful. And then now, how many elements are along the 0th axis? So elements along the 0 axis. Oh, axis doesn't have that. And we want to go rank for tensor 0 dot shape. Oh no, maybe we want shape 0. That's what we want. And then how about we want elements along the last axis. So I want rank for tensor shape. Now -1 we can use for the last axis. So instead of we have 1, 2, 3, 4 here, we could have used 3 because it's the 4th index, but we're going to use -1 just to grab the last index. That's a little trick for Python indexing. And then we want to go the total number of elements in our tensor, which will be tf size rank for, is this going to autocomplete? Rank for tensor. That should be ready to go. Let's have a look. What do we get? Okay, data type of every element. D type is a float. So, okay, that makes sense because we've got 0 dot, yep. Number of dimensions, rank 4, yes, that makes sense, 1, 2, 3, 4. Shape of tensor, yes, we've seen that before. Elements along 0 axis, so 2 elements there, yep, beautiful. Elements along the last axis, 5, that's correct, wonderful. And the total number of elements in our tensor is tf tensor 120, oh, numpy 120. Now that output can be a little confusing, so I want to show you just a trick to convert it into a NumPy integer. So you can just go here. With the tensor output, for a lot of them, you can just add .numpy on the end, and we'll watch the conversion here. So this is there, or actually we might do it with and without, just so you can see the difference. I'm just going to copy that line. Boom. There we go. So the total number of elements in our tensor, that's it coming out as a TF tensor type. But if we add the numpy on the end, we get it in this single element, which can be handy if you didn't want to have the TF tensor type. You just want the element itself. Try using .numpy at the end there. All right, wonderful. Since we now know a fair few pieces of information on how to get them from our tensors, we'll practice. One very important thing is being able to index on tensors. So we'll do a little bit of practice of that in the next video. So I'll see you then. So in the last video, we checked out how we can get various attributes from any tensor that we can create, such as the data type, the number of dimensions, the shape, and then various other attributes of it, which can be helpful when we're trying to figure out just what's going on with our tensors. Because, I mean, although we can see this one, oftentimes with neural networks, you'll be dealing with tensors that you can't actually visualize, meaning that they're so big that you won't be able to just look at them. So you need to be able to use code to find different information or different attributes about them. So now let's have a look. Say we did have a tensor like this, and we want to index it. So the beautiful thing about tensors is that, oh, we don't want that. I just want to turn that into text. So we'll go here, indexing tensors. So tensors can be indexed just like Python lists. So if you've ever done indexing on Python lists, we'll see how it relates here. But if not, that's okay, because we're just going to get hands-on as we do. That's the theme of this course. So get the first two elements of each dimension in our tensor. So if you have had experience with indexing Python lists, how do you think you might get the first two elements of each dimension of our rank 4 tensor? So remember, we've got 1, 2, 3, 4 dimensions here, and we want the first two elements. In our case, it's going to be 0 for every single one of them, but we want the first two elements of each dimension. So give that a try. If not, I'm going to start writing the code to do it, and we're going to have a look at it in a few seconds. So this is how I would get, or how you would index a tensor to get the first two elements of each dimension. There we go. So just like a Python list. So if we make here sum list equals 1, 2, 3, 4, and we want the first two elements of sum list, we go here. Use a colon, we'll get 1, 2. Beautiful. So now we can do the same, but with our tensor, we just have multiple dimensions. We separate them by column. So let's have a look at what the output of this is. Wonderful. Because our tensor is all zeros, we get 2, 2, 2, 2, and each value is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. But can you see the shape here? This is the first, the outer tensor. This is the second one on the 0th dimension. And then we have 2 here, 1, 2. And then we have 2 within these brackets, so 1, 2, and then the final 2, the elements within the most inner brackets, so 0, 0. Again, takes a lot of practice, but just look at these diagrams and start to count the tensors yourself of tensors that you can visualize. As a warning, if the tensors are too large, it'll probably separate them with 3 dots, but we'll get to that in a bit. How about if we wanted to get the dimension, or get each dimension from each index except for the final one? Now, does that make sense? So we want get each dimension from each index except for the final one. Oh, sorry, that doesn't make sense. Get the first element from each dimension, from each index except for the final one. Okay, how might we do that? Actually, let's try it with our sum list. If we wanted the first element, 1. Beautiful. Now, we want the first element from every dimension except for the final one. So let's try that. Rank 4 tensor, and we want first element from each dimension except for the last one. Will that work? We don't have the last one there. Let's try. Wonderful. 1, 1, 1, 5. Beautiful. So that means all of our tensors kind of get flattened. All the other shapes get flattened into 1, but we've still got 5. Beautiful. We can get the same thing if we add this colon here. So this colon, if it's there without a number, it just means get the whole thing. So there we go, same output as before, 1, 1, 1, 5 for the last dimension. Now if we wanted to change this up, say we wanted except for the second last one, what do you think this is going to output? If we go here, rank 4 tensor, if we want to get the second last axis, we go shape. So we're getting the first element from each dimension of our tensor except for the second last one. So what shape is this going to output if we run this line? Let's try. Wonderful. So there we go. 1, 1, 4, 1. Again, plenty of practice, but that's how we're going to learn things. So there we go. 1, 3, 1, 1. Then we could do the same here with the 0th axis. Beautiful. Okay, we'll convert that back so that comment there makes sense. Now, what else might we want to do? If we've got our tensor of this shape, sometimes what we might want to do is expand or reshape. So in this case, we've seen a little bit before on how to reshape a tensor, but let's practice changing or adding an extra dimension to the end of a tensor. So how about we create a rank 2 tensor, which has how many dimensions? 2 dimensions. So we can do that by rank 2 tensor. You can pause the video here if you want and try to create your own rank 2 tensor without me coding. But we want TF constant, my favorite numbers, 10, 7. And then how about 3, 4, because 3 and 4 add to 7. And now let's have a look at our tensor. Rank 2 tensor. We could even get some attributes about it. Rank 2 tensor, ndim. Again, lots of practice here, figuring out information about our tensors. Okay, the shape 2, yep, ndim, that's exactly what we want. Now, if we wanted to get the last item of each row of our rank 2 tensor, how might we do that? So again, let's remind ourselves what it looks like. Rank 2 tensor. Let's remind ourselves what our Python list looks like, sum list. How do we get the last element of a list? Sum list -1. So there we go. So if we want to get the last item of each row of our rank 2 tensor, well, the row comes first, so row, column. So we might go, rank 2 tensor, so the last item, -1. Does that make sense? Let's see. Does that get it? So 7, 4. Beautiful. That's what we want. If we wanted to add an extra dimension onto this shape here, so maybe we have 2, 2, 1, we can do so in 2 ways. And now this is helpful for later on when we're creating neural networks and we need to alter the size of our tensors so that their shapes line up. So it might not seem like it's very helpful now, but I just want to sort of plant the seed so that when we come across it in future videos, it's not like, whoa, Daniel, we haven't covered this method before. So let's go in here, add in extra dimension to our rank 2 tensor. So we want to turn our rank 2 tensor into a rank 3 tensor, but keeping the exact same information that is stored in our rank 2 tensor. So we're not going to change these numbers. We're just going to change the shape that the numbers fit into. And we can do that by going here, ... Now this is a little bit of fancy notation. You might not have seen this before. We can go tf dot new axis. Let's see what this does. Oh, we need to visualize our tensor, don't we? Beautiful. So you see what that did there? That's now added a dimension on the end of 1. So let's look this up, tf.newAxis. tf tensor. If we search, again, I'm just pressing Command F, you might press Control F, tf.newAxis. There we go. So 1 of 8, it appears 8 times. So insert another dimension. Does it have the actual definition here? Notes tf new axis is none as in numpy. So if you're using numpy, you probably use none. In TensorFlow, it's tf.newAxis. doesn't actually say what it does. Sometimes where you'll find the documentation, it can be quite hard to sometimes find the exact definition of this method, but you can kind of deduce what it does by running through the examples as we see here. So let's go in there. It's better off just to remember, if in doubt, write the code, try it out. So the other alternative to using this, oh, by the way, these 3 dots means on every previous access to this one. So this means instead of just going like this, so see how we've got access 0, access 1, access 2 in this case, add an access on the very end. We can just scrap these and go every access before the last one, include those because that's ... and add a new access on the end. So the other alternative to tf.newAccess is alternative to tf.newAccess. You might also see tf.expandDims. So that stands for expand dimensions. And then we're going to pass it rank 2 tensor. And then we want to expand it on the final axis. So -1 means expand the final axis. There we go. We get the exact same output as this notation here. It's just slightly different. So if we want to go here, tf.expandDims. There we go. We got some documentation for this one. So we have the input. We come down. It says, what is the input? The input is a tensor, and the axis is integer specifying the dimension index at which to expand the shape of input, giving an input of d dimensions. So if we come back here, what do you think will happen if we go axis equals 0? So look at our shape there. What I might do is keep that there. We're going to retype this out. tf expand dims rank 2 tensor. We want as much practice as writing TensorFlow code as possible, right? So expand the 0 axis. So let's try that. Boom. So now, instead of being on the end, our extra dimension is at the front, and then we can even change it. We want the extra dimension in the middle. Wonderful. And then if we want to put it on the end, we can go -1. Beautiful. So we might put that there. Expand the 0 axis. And so notice, even if we run this and we check out rank 2 tensor, the numbers inside stay the same, 10, 7, 3, 4, except the dimensions change. So how those numbers are stored changes. We've covered a fair bit in terms of getting information from our tensors and also indexing our tensors. Now let's have a look at how we might. We've actually done a little bit of manipulation here too, but the next videos, we might go through manipulating tensors. In other words, known as tensor operations. So if we do have elements within our tensors, how do we manipulate those and how do we combine them into different ways? So go back through, practice expanding the dimensions of tensors, practice getting different attributes from tensors that you've created. And then in the next video, we'll see what kind of tensor operations we can work with. If your data is stored in some sort of tensor format, finding patterns in those tensor formats often involves manipulating tensors. Now, again, when building models in TensorFlow, much of the pattern discovery within tensors is done for you. However, oftentimes that pattern discovery is through the extended use of a few basic operations. So let's start getting into those, otherwise known as tensor operations. We'll start off with basic operations. Now, do we have a tensor? So you can add values to a tensor using the addition operator. And by the way, when I say basic operations, I'm talking about the default Python operators such as plus, minus, multiplication, and then if we want divide, we can go like that. Right, so we can add values to a tensor using the addition operator. So let's create a tensor equals tf constant, and we might make it 10, 7, my favorite, and 3, 4. And now if we go here, plus 10, what do you think will happen? So this is our tensor here. And if we just use the basic operation of tensor plus 10, wonderful. We get 10 plus 10, is 20. 7 plus 10 is 17. 3 plus 10 is 13. And 4 plus 10 is 14. Wonderful. Now you'll notice that the original tensor is unchanged. This is important because when we're manipulating tensors, we don't necessarily always want to change the underlying tensor. The only way it'll change is if we go tensor equals tensor plus 10. We'll reset it. Now this is going to be plus 20, isn't it? There we go. We'll come back here. There we go, tensor. But if we got rid of this, tensor, we rerun this cell. Oh, invalid syntax. And then we rerun this one. We still get the same values as what our original tensor was. And we might just press enter there so it's more succinct with how it comes out. Beautiful. So, of course, other operations also work. So multiplication also works. So if we wanted to go tensor times 10, same thing. We get 100 because 10 times 10, 100, 70, 30, 40, etc. And then subtraction if you want. So tensor minus 10 can go into the negatives. That's no problem. Tensors can store a whole range of different values. In addition to the operators, like the Python operators, we can also use an equivalent TensorFlow function. Now, what this means is that if we do use the TensorFlow function, so that means we're accessing the TensorFlow library. Let me just show you, because it's easier to talk about something if we can see it. We can use the TensorFlow built-in function too. So tf.multiply, and we want, see here, we get the doc string here. We get tf.mat.multiply, so we'll have a look at that in a moment, but I just want to demonstrate it to you. Tensor 10. We get the same output here. So if we go here, let's look up tf.math.multiply. So for a lot of these tf.math functions, so tf.math, we can do the alias of just tf multiply. So if we go tf multiply, it's just going to lead us to the same thing. Wonderful. Now, does it say here what the benefits are? It doesn't quite. But what I'm going to get you to do is just trust me here when I say that if you have to do some sort of tensor operation like this, and again, usually a lot of these will be done behind the scenes for you. But if you want your code to be sped up on a GPU, typically it gets sped up when you use the TensorFlow version of some sort of operator. So if we wanted to do addition, I mean, this is going to be very fast because it's only a small tensor. And we could do tensor plus 10. But if you want to have the advantages of TensorFlow built into your basic operations, use the TF math something tensor to manipulate your tensors. But here, again, even though we've used the TensorFlow function here, the original tensor is still unchanged. So these are the basic operators. Create some tensors, have some practice at running the addition, minus, multiplication, and division on them, and also do the equivalence of tf.multiply or tf.addition or something like that. Is it tf.addition? tf math addition? Or is it just add? Yeah, add. Okay. That's your little homework for this brief video here. But in the next one, we're going to have a look at a very important concept in neural networks, and that is matrix multiplication. We'll see how to do that with tensors. So we left off in the last video figuring out how we can manipulate our tensors with the basic operations. And so hopefully you've tried out a few of these for yourself. But now we're going to go on to matrix multiplication. So in machine learning, matrix multiplication is one of the most common tensor operations. So the ones we've been through already, these basic operations, are often referred to as element-wise operations. So that means that if we go here, for the addition, for example, we've got our tensor here, which is 10, 7, 3, 4. Now, element-wise means go through one element at a time and just add 10. So this element, add 10. This element, add 10. This element, add 10. This element, add 10. But there's a few different types. So matrix multiplication and the dot product are not necessarily element-wise. So if we go here, what is matrix multiplication? How to multiply matrices. Math is fun. I really like this domain name, actually. Let's have a look here. A matrix is an array of numbers. To multiply a matrix by a single number is easy. So 2 times 4 equals 8. Yes, that's what we've done, right? So that's element-wise. So 2 times 0 equals 0, 2 times 1 equals 2, 2 times negative 9 equals negative 18. Beautiful. However, what if we wanted to multiply a matrix by another matrix? And remember, because we're using TensorFlow, even though this is a matrix, we're referring to them as tensors as well. So I want you to read this as matrix and tensor interchangeable. But to multiply a matrix by another matrix, we need to do the dot product of rows and columns. What does that mean? Let's see an example. So the dot product is the first row and the first column. Okay, so we've got a row here times this column equals 58. Okay. The dot product is where we multiply matching members, then sum them up. So 1, 2, 3 times 7, 9, 11. Okay, 1, 2, 3 times 7, 9, 11, yes. Equals 1 times 7. Okay, yep. 2 times 9. Yeah, 2 times 9. 3 times 11. Okay, I've got that. That equals 58. Then we do it again for the second column, and that's 64. And then again, again, again. A great website I like to visualize this is, I believe, matrix multiplication.xyz. We'll go to that. So here, beautiful. We can even customize these. So we'll go here, 1, 2, 7, my favorite number, 7, 2, 1, just to be fancy. And then maybe 3, 3, 3, because I like 3 as well. And then this can just stay the same. So might zoom in here. So let's go multiply. What happens? Whoa, we get some. So that tensor just came up there and jumped on top of that. And then if we go through, we go 1 times 2, 2 times 6, 7 times 1. Okay, so that's 2 plus 12 plus 7. How did this get to 21? 2 plus 12 plus 7. We might try a different set of numbers. How did that work? 5. Maybe our matrix multiplication demo is busted. Multiply. Let's try. 1 times 3 plus 12 plus 5. Does that make sense? So 3, 12 plus 5. Yeah, that makes sense. 15. So this is 3 plus 12 is 15 plus 5 is 20. There we go. And if we step through there, step through, wow, we get the output there. Before we even start to write code, go to this website, start practicing around, see what happens. And after you've done that for about a minute or so, or maybe 3 minutes, give yourself a few different goes. Let's go back to the notebook and see how we can do this exact operation in TensorFlow code. So I'll give yourself a second there, but I'm going to start coding so you can pause the video now if you want, try out that website and come back. So let's see matrix multiplication in TensorFlow. What if we just Google that, matrix multiplication in TensorFlow? matmul, there we go. tf.linalg, which is short for linear algebra, .matmul. Multiplies matrix A by matrix B, producing A times B. A, B. And we get a whole bunch of documentation, which is beautiful. We could read through that, or we could write the code ourselves. So, what do we have? Do we have a tensor? Print our tensor. We can print it if we want. Print, yes we do. Now tf matmul. Now for a lot of these operations, you can usually drop the intermediary here. So linalg. This is a little trick of TensorFlow. You can just do tf.matmul, which is what I'm about to do here. tf.matmul, tensor, tensor. Can we matrix multiply those? Oh, yes, we can. Wonderful. We get 121, 98, 42, 37. Beautiful. Now, if you wanted to do the matrix multiplication, Python has an operator, A. Now you see how the outputs here actually are different to if we just did, what if we did tensor times tensor? We get different outputs here. Okay. Because if we have a look at our tensor again, this is element-wise. So it's just gone 10, maybe we'll print it out twice. 10 times 10 is 100, 7 times 7 is 49, 3 times 3 is 9, 4 times 4 is 16. Whereas with matmul, we've gone in this fancy little way here. So maybe, I've got an idea, we recreate this tensor. That could be a little exercise for you as well, is to recreate this tensor in TensorFlow and recreate this tensor in TensorFlow. So the same elements in the same shape. This would be a what? 1, 2, 3, a 3 by 3 tensor. And this would be a 1, 2, 3 by 2 tensor, so 3 by 2. And then run tf.matmul on left tensor, right tensor. See if you get the same outputs as here. But we come back here. If you wanted to do matrix multiplication with a Python operator, we can do tensor at tensor. So the at symbol in Python actually is for matrix multiplication. Now, both of these examples work because our tensor variable, this is an important fact, this is where we come in and we check the shapes attribute. Because our tensor.shape attribute is 2 and 2. So both of them have the same shape of 2 and 2. But what if we wanted to do matrix multiplication on tensors which had differing shapes? Now, rather than just think about it, let's try. So create a tensor of maybe 3, 2. Similar to this one here. So this is 3, 2. Remember, rows come first. 1, 2, 3. Columns, 1, 2. Let's create a similar one. Create a 3, 2 tensor equals tf constant. And we want 1, 2. We'll keep this one nice and simple. 3, 4, 5, 6. Beautiful. And then we want create another 3, 2 tensor. And in this case, it can be y, tf, constant, and we'll just increase this one. So that can go from 7, 8, 9, 10, 11, 12. Wonderful. Let's have a look at both of those. X, Y. Okay, so we've got two tensors here, both of the same shape, 3 by 2, and they got slightly differing elements. Now, what if we tried to matrix multiply them? So let's try to matrix multiply tensors of same shape. We could do it like that. See what happens. Oh, matrix size incompatible. In 3, 2, in 3, 2. What if we try the TF matmul? What happens here? X, Y. Invalid. Matrix size incompatible. Same thing. 3, 2, in 0. So this is our first element here, our 0th element. And this is our other element here, our first element, which is also 3, 2. This is where we have two rules for matrix multiplication. Do these websites tell us? Why do we do it this way? Actually, this is a great example. I'm going to put this as an external resource if we come back. If you ever see this emoji in the course, this is a resource. So resource, info, and example of matrix multiplication. So check that out. If you ever see that little book emoji, that's an external resource that I definitely recommend. Now, let's go back to here. Why doesn't this work? I don't think this web page explicitly states it, but I'm going to tell you anyway. You can look this up. You'll find this wherever you find matrix multiplication, is that there is a couple of rules that our tensors or matrices need to fulfill. So come up here. Let's put in here. There are two rules. Our tensors or matrices need to fulfill if we're going to matrix multiply them. Now, rule 1, the inner dimensions must match. And rule 2, the resulting matrix has the shape of the inner dimensions. So knowing these 2 rules, I'm going to set you a challenge. Before the next video, we're going to go through these 2 rules and see how we can fix our problem here. But considering these 2 tensors, so we've got, if I say rule 1 is that the inner dimensions must match, what are the inner dimensions here? Maybe 2 and 3, they don't really match. So how would we get the inner dimensions of these 2 matrices to match? That's your challenge. If you're not sure, that's completely fine, but that's your challenge before the next video. If you can get it done, amazing work. If not, we're going to go through that in the next video. So I'll see you there. In the last video, we kind of left off on an error. And we said in this video that we're going to fix it. So let's do that. Now we tried to matrix multiply 2 tensors of the same shape, specifically x and y. They're both of the shape 3, 2. We've got this little error here, saying n0 is 3, 2 and n1 is 3, 2. So matrix size incompatible. So if we come up here, back to the rules we set ourselves, the inner dimensions must match, and the resulting matrix has the same shape of the inner dimensions. Now, if you had a go at fixing this and you got through it, excellent work. You may want to skip over this lecture. However, if you didn't make it, that's completely fine. Matrix multiplication takes a little while to get your head around. If we come over here, I've got a slide. Matrix multiplication is also known as the dot product. So when we call the code tf.matmul, and we have a matrix of some size here, and a matrix of some size here, remember, a lot of the operations that we do can be on matrices or tensors of an arbitrary size, but just for illustration purposes, I've done this size here. So here's our first rule. So numbers on the inside must match. And there's our second rule. New size is the same as outside numbers. Okay. So if we come back, does that line up with what we've said here? The inner dimensions must match. The resulting matrix has the same shape of the inner dimensions. Oh no. Of the outer dimensions. There we go. Getting our own rules incorrect. So we come back. Let's have a look at what's going on here. We've got tf.matmul. We've got one matrix or tensor here, A, B, C, D, E, F, G, H, I, which is the shape of 3 by 3. Wonderful. And this will run because the numbers on the inside match. See these 2 3s here with the red background? And this is of shape 3, 2. So 1, 2, 3, and 2 columns. Okay, so that matches. And then we're going to result in here. If we did the dot product, which is the same as matrix multiply in TensorFlow, we have A times J plus B times L plus C times N, and then we follow through with that rule for every single cell in these 2, or every single element in these 2 tensors. And now the new size is 3 by 2. 1 row, 2 row, 3 row, 2 columns, which is the blue numbers here. Okay, wonderful. And then if we swap these elements from letters to actual numbers, so the same shapes here, we take 5 times 4. Okay, this is the same as A times J. Yes. 0 times 6. Okay, 0 times 6. Yes, which is the same as B times L. Wonderful. And then we have 3 times 8. Which is the same as C times N. All right. Now, again, looking at these diagrams, they're quite, for the first, I would say, 20, 30, 50 times you look at dot products and matrix multiplications, it takes a lot of repetition to get used to. But then if we have 5 times 4 equals 20, plus 0 times 6 equals 0, plus 3 times 8 equals 24, so we add these 3 up, we get 44 in the top left. Repeat the same for each element, and we get this resulting matrix here. Now, the live demo we've already had a look at. Matrix multiplication.xyz. This is what's happening here. If we reset and multiply, we take that, we flip it on the top, then we go here, we get 20, and we get the next 2 elements, and the next 2, and the next 1. So this is a moving diagram of what's going on here. So let's go back to our code. Let's fix it up. Let's make it work. So knowing our two rules, number one, that the inner dimensions must match, and that the resulting matrix is the same shape as the outer dimensions, how might we get this to work? Well, we're either going to have to change the shape of this matrix or change the shape of this matrix. Again, I'm using the term matrix and tensor interchangeably here. Or we're going to just have to create an entirely new tensor with the same shapes on the inner axes. So let's see it in action. Let's change the shape of y. So we can change a shape using tf.reshape y, and then we enter the shape that we'd like. In our case, it is currently 3, 2. So maybe we change it to 2, 3. And let's see what happens. Ooh, wonderful. Let's see the original y. Beautiful. So we can see that the 9 has come up to here in this one. And we've now got 10, 11, 12. So this has got 2 rows and 3 columns. Okay. So maybe we go try to multiply x by reshaped y. So x, and we might have to put matrix multiply here so we know what type of multiplication we're doing. X, tf, reshape y, and then shape 2, 3. Now you see what's happening here? So if we remind ourselves what shape x is shape 3, 2. Let's pay attention only to the shapes. tf.reshape y shape equals 2, 3 dot shape. Paying attention to our rule that the shapes of the inner dimensions, so this tensor multiplied by this tensor, the inner dimensions must match. Does that rule get fulfilled? To me it does, because we've got an inner dimension of 2 here and an inner dimension of 2 here. Let's test it out. Beautiful. It looks like that worked. So we come here, we want to make a new cell. What if we tried to use tf.matmul on this? So if we go tf.matmul x tf.reshape, and then we want y shape equals 2, 3. Is this going to work as well? Beautiful. Now we get the same outputs there. Now hold on. Now do you think if we were to reverse this, it would work as well? Now I mean we reshape x to be a different shape instead of reshaping y. If in doubt, code it out. So x tf reshape x, we're going to change that to be 2, 3 this time. And we're going to not change the shape of y. Let's see what happens. Ah, what happened there? So let's see. We'll just put a little note here. Try change the shape of x instead of y. So you see here how this one has the shape 3, 3, but this one has the shape 2, 2. That's because in this operation, we multiplied 2 tensors with the shape 3, 2 and 2, 3. So the resulting tensor finishes with the dimensions of the outer dimensions. Whereas in this case, if we go tf.reshape x, shape equals 2, 3, y dot shape, we also want the shape here. This is our other rule of matrix multiplication. Because we reshaped x, the resulting matrix here ends up in a shape of 2, 2, because it becomes the outer dimensions. So see here, back to our rule, numbers on the inside must match. New size is the same as outside numbers. Okay, so in both these cases, depending on which tensor we reshaped, the matrix multiplication works, but the resulting output is different. Now, that's a very important point. When you're dealing with matrix multiplication or dot products, it really depends on which tensor you manipulate in terms of what your output would be. So see here how different these two outputs are. again, we're multiplying the same numbers, but just in different shapes. So that's an important concept to be aware of. And now we can do the same thing with reshape as with transpose. So let's have a look. This is another important tensor transformation. So we can do the same with transpose. However, as you'll see in a second, transpose is slightly different to what reshape is. So transpose, and if we do TF reshape X, shape equals 2, 3. So this is the transpose tensor. They're the same shape as reshaping it. However, you'll notice with the transpose is that, well, let's get X, the first one as well. It starts off as 1, 2, 3, 4, 5, 6. Then the transpose is 1, 3, 5. The odd ones are up the first row. And then 2, 4, 6. And then the reshape is 1, 2, 3, 4, 5, 6. So the difference between transpose and reshape is that transpose flips the axes, whereas reshape just shuffles the tensor around into the shape that you want. So if we go here, TensorFlow transpose, TF transpose, here we go. Transpose A, where A is a tensor. Wow, that's a great description. Permutes the dimensions according to the value of perm. The returns tensor's dimension I will correspond to the input dimension perm I. If perm is not given, it is set to n minus 1 to 0, where n is the rank of the input tensor. Hence, by default, this operation performs a regular matrix transpose on 2D input tensors. Okay, so we see here 1, 2, 3, 4, 5, 6, transpose. Now the shape is 3, 2. Again, we could try a bunch of different examples, but let's go back and write some different code here. So what we might want to do is, because transpose also changes the shape of our X tensor, let's try matrix multiplication with transpose rather than reshape. So TF matmul, TF transpose X and Y. What might be the output here? Let's find out. 89, 98, 116, 128. Now see how that is different here? Now that is because transpose flips the axes rather than shuffles around the elements of a tensor. This can be quite confusing. However, this kind of data manipulation is a reminder that you're going to spend a lot of your time in machine learning and neural networks reshaping your data in the form of tensors to both prepare it to be used with various operations such as feeding into the model, and once you get it out of the model, to be able to deduce patterns from it and convert it into something human understandable. Now, again, the numbers that we're dealing with are just basically toy numbers. To see an example of how matrix multiplication is actually used, this is a great example. This may seem an odd and complicated way of multiplying, but it is necessary. I'll give you a real-life example to illustrate why we multiply matrices this way. So, example, the local shop sells 3 types of pies, and then we have details here. And if you go through this, this is actually a dot product to work out the value of sales for any given day. Now, this is just a small example here, but in the case of neural networks, they're actually going to go through an absolute multitude of these different numerical transformations to find patterns in our data. The good news is, most of the time, is that once we've set up our neural network code, once we've gotten our tensors into the right shape, a lot of these are done behind the scenes for us. So, with that being said, let's finish this video here. And in the next video, we'll go through a little bit more. We'll really cement down, or we'll get some more practice with transposing and reshaping different matrices and practicing matrix multiplication. So I'll see you there. We've had a little bit of hands-on practice with matrix multiplication and transposing and reshaping different tensors. We're going to do one more video on it to really nail it down. So let's call this one the dot product. And we want to turn that into a markdown cell. Beautiful. So let's go here. Matrix multiplication is also referred to as the dot product. And now you can perform matrix multiplication using, we want tf.matmul matrix, which is short for matrix multiplication, or we can do it with tf.tensor. We haven't seen this one yet, but they essentially do the same thing, just with different parameters. So we come here. We've also gotten hands-on with matrix multiplication using matrix multiplication.xyz, and we've seen this colorful example of the dot product. But let's once again get a little bit more hands-on with some code. So let's see how we might use tensor dot. Again, I'm spelling tensor wrong. I'm going to do that throughout this whole course, aren't I? There we go. So perform the dot product on x and y. Now this requires x or y to be transposed. We've also seen how transposing results in different outputs than reshaping. And transposing is flipping the axis, whereas reshaping is just reshuffling. So if we come here and if we reset this, I want you to have a guess at what type of operation this is. Is this a reshape if I go like that and flip it? Or is that a transpose? I'll give you a hint. What did we do? We had to flip the axes to get it up like that. So in that case, it's going to be a transpose. Now, let's use tf tensor dot. And actually, before we do that, let's remind ourselves of what x and y are. X is a tensor of shape 3 and 2, and y is a tensor of shape 3, 2. They have increasing elements from 1 through to 12. Beautiful. Now, if we go tf transpose x and y, oh, I've typed y as a mini case. There we go. Tensor dot, oh, missing argument axes. So we want to type in on the first axis. Beautiful, 89, 98, 116, 128. Now, if we look up tf tensor dot, what is this going to tell us? Tensor contraction of A and B along specified axes and outer product. Tensor dot, also known as tensor contraction, sums the product of elements from A and B over the indices specified by A axes and B axes. Now, again, you can read through this if you'd really like to, or you can practice coding it. I would suggest doing both. Now, in this case, you might notice that we could use transpose or reshape. However, we get different results. Now, let's try matrix multiplication by transposing y and reshaping y. We've done it with x. Let's try it with y. So, perform matrix multiplication. There's going to be a lot of repetition when manipulating tensors because we want to get practice. Y transposed. So tf matmul, let's take x and we'll transpose y. Transpose, there we go. Now perform matrix multiplication between x and y reshaped. tf.matmul. You might be wondering why I'm just continually showing you different ways of manipulating matrices. It's because you're going to spend a lot of your time reshaping tensors and matrices into the shape that you want them. So if we can get as much hands-on experience as we can, it might not mean too much to us now because we're just working with toy data. It means later on down the track when we have to reshape and manipulate our tensors and matrices, is that we've got all of this practice under our belt. Wonderful. So we see we get different results from transpose and reshape. Now, to really demonstrate the fact here, or the fact that calling reshape and transpose on y don't necessarily result in the same values, is that we're going to go through the same steps we did up here before for x. But let's make it a little bit more pretty. So check the values of y. This is how I really try to understand things. And transposed y. So if I am writing some code, as I've said before, and I'm wondering why I'm getting different outputs of my tensors and the calculations that I'm making aren't really sort of making sense in my head. By the way, this /n is for new line. As I've said, one of the most common errors you're going to get in writing neural network code is misshaped tensors, and even more like sort of just as common, but deceiving error that is when your tensors line up with shape, but the outputs that you're getting, so you get no error message, it just works. So it's important then to be able to investigate what's going on and figure out, that's called a silent error, is that when your code works, like no error gets outputted from the code itself, but the results just clearly aren't correct. So this is the sort of thing that I will do to investigate those silent errors. TF transpose Y, that's what we want to do. So I'll create some sort of print statement like this, and then I'll use this to really get my head around what's going on. So this is our normal Y, 7, 8, 9, 10, 11, 12, beautiful. Now this is reshaped, again, just reshuffled. We bring the 9 up here, we move the 10 across, the 11 comes up there, the 12 goes on there, so 7, 8, 9, 10, 11, 12, beautiful. Now this is the transposed, so all we've done here is just flip the axes. Let's recreate this one, nice and simple. So 7, 8, 9, 10, 11, 12 over here. We'll just let that run through. This is a great way to just visualize. Let me reset this. 7, 8, 9, 10, 11, 12. Okay, we come back to this tab. You see how we've just got the same tensor here, 7, 8, 9, 10, 11, 12. This is the same over here, beautiful. Now watch, this is a transpose. We're going to bring this up, flip it, boom. That's what has happened here. You see? Except this one is upside down in this case. So it just displays it slightly differently, but the shape and where the values end up, in this case, is what's going to happen if we were to write, say, some code like this. So if we go tf.mapMul, x tf transpose y. Beautiful. There we go. So this is a sort of investigative work that we do. We've had a fair bit of practice now transposing and reshaped. If you're still unclear what the difference is between transpose and reshape, or you're wondering, which one should I use? Well, most of the time, these operations will be done behind the scenes for you. So if you write neural network code, it's going to do a lot of matrix multiplication behind the scenes to figure out different patterns in numbers. What sort of patterns are they? Well, remember, here's a simple example of the kind of patterns you can work out with matrix multiplication. But again, it'll be different depending what problem you're working on. But generally, whenever you're performing a matrix multiplication on two different tensors and the shapes of the matrices or tensors don't line up, you will transpose one of the tensors rather than reshaping them. So I'll write that here. Generally, when performing matrix multiplication on two tensors and one of the axes doesn't line up, you will transpose rather than reshape one of the tensors to satisfy the matrix multiplication rules. Alrighty. So again, if there's anything that doesn't quite stick out or make sense, I would definitely encourage you to create a whole bunch of different tensors. Try to use TF mapMul on them. Try to use tensor dot if you want, or try to even use the @ operator between them. Generally, if we're using TensorFlow, we're going to be using mapMul. But get some errors, fix the shapes with transpose and reshape, and see what kind of different outputs you get. So we've covered matrix multiplication. Now let's have a look at, if we've got the default data type is often int32. So sometimes, depending on what data we're working with, the data type might not be int32. So what if we had to change the data type of a tensor? That's what we'll look at in the next video. I'll see you there. All right, so as we said in a previous video, the default data type of most tensors will be int32, depending on how they've been created. However, sometimes you'll want to change the data type of your tensor. So let's see how we'll do that. So we can create a new tensor with the default data type which is float 32. Yeah, let's start off with float. Now, I just said that the default is int 32, but if we go, the default data type will actually depend on what data is inside your tensor. So if there are floats inside your tensor, we will have b.dtype tf float 32. Now if we create c equals tf constant, now in here we want 710, and this is going to be c dtype int 32. Wonderful. So in the current version of TensorFlow that I'm using, which is tf, I believe it's 2.3 version, 2.3.0, you may have a slightly different version depending on when you're watching this video. At this time, if we create a tensor with floats inside it, they're going to be a float 32 type. And if we create a tensor with integers inside it, they're going to be of tf.int32 type. Now, let's say if we wanted to change from float 32 to float 16. Now, this is called reduced precision. Let's go 32-bit precision. What does this mean? So I'm reading a book about OpenGL ES development. A float in Java has 32 bits of precision, while a byte has 8 bits of precision. This might seem like an obvious point to make, but there are 4 bytes in every float. Okay. So that's in Java. That's not what we want. So 32-bit precision tensor versus 16-bit precision tensor. Mixed precision. Here we go, TensorFlow. Why did we ever doubt the TensorFlow documentation for having something? Mixed precision is the use of both 16 and 32-bit floating point types in a model during training to make it run faster and use less memory. Okay. By keeping certain parts of the model in 32-bit types for numeric stability, the model will have a lower step time and train equally as well in terms of evaluation metrics such as accuracy. Using this guide, this API can improve performance by more than 3 times on modern GPUs and 60% on TPUs. Today, most models use float 32D type, which takes 32 bits of memory. There we go. However, there are 2 lower precision D types, float 16 and B float 16, each which takes 16 bits of memory instead. Beautiful. Modern accelerators can run operations faster in the 16-bit D types. Okay, so the main takeaway from this is that in TensorFlow, the default is 32-bit precision, right? However, we can also do, with modern pieces of hardware, we can also do float 16, which takes 16 bits of memory instead. And modern accelerators, which are talking about hardware accelerators, so when we run our code on hardware, can run operations faster in the 16-bit D types. That is what's exciting. So, in our case, if we wanted to change our numbers from 32-bit precision, in other words, storing this tensor in 32 bits on memory, we wanted to change it to float 16, how might we do that? Well, let's have a look. We can use tf.cast, and then we're going to pass it our original tensor, and then its new D type is going to be tf float 16. Oh, and then we want to do B, find out B. Wonderful, D type equals float 16. The original B, what we might do is type out B, and then B.D type. So we'll reinstantiate B up here, or maybe it's better just to go D here. Yeah, that's a better idea, Daniel. Wonderful, look at that. We got float 32, and now D is the same as B, but it's been stored as float 16. So, again, might not matter too much for tensors of only 2 elements, but if we had a tensor of 1,000,000 elements, and we reduced the floating point size from 32 to 16, we've basically halved the amount of space our tensor is taking up on memory, allowing a hardware accelerator to make calculations on it, potentially twice as fast. Now again, that scale may be different because there's a lot of different things that go into computing scale and speeds and whatnot, but that's the concept I want you to imagine, is that although these numbers here take up less space on memory, they may be able to compute faster. And the same thing goes for if we wanted to change from int 32 to float 32, we can do it in a very similar manner. So Let's go change from int 32 to float 32. So we can go e equals tf cast. Which one do we make? C d type equals tf float 32. Now let's have a look at e. Beautiful. So C was originally, there we go, d type equals int 32 and 710. We just changed it using tf cast. So E is now, take C and turn it into a float 32. Beautiful. And now we can take E float 16 equals tf cast E d type equals tf float 16 E float 16. Wonderful. So there are many different data types in TensorFlow. So if you ever come across the need to change your data type of a tensor because some calculations aren't working correctly, tf cast is going to be your friend. So with that being said, let's have a look in the next video. We're going to go aggregating. We'll see what that means. So have a play around with this one. Create some tensors of float type, of integer type, and then change them from, you can go from float 32 to float 16, or you could go from int 32 to float 32. See how many different combinations of data type you can create and change before we see how we can aggregate our tensors. Welcome back. Now, after the last video, I took another little break. And so what you see here is when the cell numbers are empty. I just want to show you this. This is, rather than going straight onto the next video in practice, I just want to show you how I actually work with Google Colab notebooks every day. Is that when you leave it for a while, all your information in Colab is going to shut down so that Google's compute resources can be allocated to other people who want to use Colab. So you see here, I haven't got a connection. But if I decide to run a single cell, Shift and Enter, it's going to allocate some memory to me. Basically a computer in Google's warehouse full of computers somewhere around the world. And once it's ready to go, boom, we're connected. However, if I try to run this cell above here, TF is not defined, so I haven't imported TensorFlow. So what I often do is, we saw this in a previous video, but it'll work better now because, see here, we've got 0, 1. These are the first cells I've tried to run in this notebook since taking a break. Let me do, if I wanted to run, I could do restart and run all, so that would run all the cells in this notebook, or I could just do run before, which is what I usually do. It's going to try and run all of the cells before whichever current cell that you're on. But boom, we get our type error right back up the top here where we created our changeable tensor with tth variable and we deliberately caused an error. So if that happens, your errors are not going to fix themselves, but then we can just go back to here and then we should be able to run all of our cells. I'm just continually pressing Shift and Enter. Should be pretty quick because we're not processing much data here, but we'll go right down to where we were, aggregating tensors. Oh, we got another error. That's all right. We'll keep going. Oh, we've covered a fair bit of ground here. Are we at? Yes, here we are. So we're back to where we were. So aggregating tensors. Now let's have a look. What does aggregation mean? Define aggregation. A group, body, or mass composed of many distinct parts or individual. A galaxy is an aggregation of stars and gas, the collecting of units or parts into a mass or whole. The condition of being so collected. Well, that doesn't really help us with understanding tensors, but we're going to see hands-on what aggregation means in the concept of, or in the topic of tensors. So to me, aggregating tensors equals condensing them from multiple values down to a smaller amount of values. That's how I conceptually understand aggregation. You can create your own definition, and in fact, I actually want you to start doing that more and more with, as you get more familiar with the world of deep learning, is to, of course, there's going to be agreed upon definitions in the field, but I also want you to start conceptualizing your own definitions in a way that you best understand things. But let's see how we might start aggregating our tensors The first way we're going to do is by getting the absolute values. So this is actually probably not the best form of aggregation to start with, but we're going to include it here anyway, just for completeness. So we create a tensor. What were we up to? E. We might recreate D here, TF constant, just because Daniel begins with D, and it's aside from the number 7, D is probably my favorite. Sorry, number 7 is probably my favorite number, and D is probably my favorite letter. So fun fact about me. There we go. Get the absolute values. Beautiful. So, we just created a new tensor, and if we wanted to get the absolute values, we can go tf.absd, and we'll see what this does. Beautiful. So the absolute values are basically just take all the negative numbers in one tensor and turn them into positive numbers. So if we see here, let's check out the docstring. I'm pressing Shift Command Space to get this docstring. Computes the absolute value of a tensor. Given a tensor of integer or floating point values, this operation returns a tensor of the same type where each element returns the absolute value of the corresponding element in the input. Beautiful, such a formal definition. And then we've got some example use cases. So let's actually start to see a few more versions of aggregation. Let's go through the following forms of aggregation. We'll turn that into a markdown cell, and we'll come down here. The first one I want to go through is get the minimum, and then we might want to get the maximum of a certain tensor. We might want to get the mean of a tensor, and we also might want to get the sum of a tensor. Now, I've shown you a few different ways of how you can explore different methods in TensorFlow. So if you wanted to start with a tensor and find the minimum, the maximum, the mean, or the sum, how might you research? So if we go here, find the mean of a tensor in TensorFlow. Here's a little hint. If you were to search that, you can pause the video now, skip and go ahead and try to create your own tensor, do these 4 things, and then come back and we'll compare notes, all right? But otherwise, if you're going to watch on, let's start by creating a random tensor so that we can practice each of these 4 things here. Create a random tensor. We might create a larger tensor. Yeah, how about we do that? With values between 0 and 100 of, how long should we do it? Of size 50. Let's do that. So E equals TF constant. We'll do it using a NumPy random array. So again, this is going to just be return random integers from low inclusive value to high exclusive value. So we can just go 0 to 100 size equals 50. Now this should give us a tensor. Beautiful. 50 values between 0 and 100. And we might go E, how do we check the size of our tensor? Let's practice. And then how do we check the shape of our tensors? And then how do we check how many number of dimensions our tensor has? Beautiful. So we get size is 50, beautiful. The shape is also 50, and the number of dimensions is 1. All right. Now, how about we start with finding the minimum? So we're going to go find the minimum. To find the minimum of a tensor, you can do reduce min, pass it a tensor. Put the output there. Now, this is going to be a little bit of a trend with TensorFlow aggregation, is that the reduce underscore, in some, like NumPy, if we did MP min, I believe, we can just go 0. But TensorFlow tends to put reduce underscore min in front of its aggregation methods here. So we'll get rid of that one. So knowing that this is the way to find the minimum, how do you think we might find the maximum? Let's find it anyway. Find the maximum. TF reduce max. Wonderful. So there's 97. So that makes sense because we have values between 0 and 100. So our lowest value so far is 0 and the highest value is 97. and find the mean. Let's go TF reduce mean of E. And wonderful. So 48 is about the average. So get the sum of a tensor. Let's have a guess. Find the sum. TF reduce underscore sum of E. And there is the sum of our tensor. Beautiful. Now, there's a few other things that we can do, such as I'm going to put a little challenge here. I want you, of our E tensor, before the next video, I'm going to put a little emoji here. Exercise is to, with what we've just learned, find the variance and standard deviation of our E tensor using TensorFlow methods. So, if you're not sure what variance and standard deviation are, this challenge has two sides to it. First, you have to find the code to find the variance of our E tensor, and then you have to look up what variance and standard deviation are. So, go and give that a try, and I'll see you in the next video. We finished up the last video with a little challenge. So, did you figure it out? Did you find the variance and standard deviation of our E tensor using TensorFlow methods? I hope you gave it a try, but if not, we're going to check it out here. So find the variance of our tensor. Now, as you might have guessed, we can do TF reduce var E. Oh, has no method reduce var. Is it variance? Has no method reduce variance. Oh, TensorFlow variance. I typed TensorFlow wrong. Ah. Okay, we can do the reduced standard deviation. Have I led you on a wild goose chase? Yes, I totally meant for all this to happen. TFP. So what we might need to do is, what's TFP? This is what I like to do, is just figure out, go down the rabbit hole. TFP, TensorFlow probability. Okay. How do we import it? Can we do import TensorFlow probability as TFP? There we go. And then we might do tfp.stats.reduce variance of E. What was that method again? We come back here. This is the type of research I want you to start practicing. Okay, tfp.stats.variance. There we go. Wonderful. Okay, so there's the variance there. I'm going to put here, won't work. And then if we wanted to find the standard deviation, so let's put a little note here actually. To find the variance of our tensor, we need access to TensorFlow probability. And then we go here, find the standard deviation. See, I thought that you would be able to just do reduce variance. So I've learned something there too. Apparently, we need TensorFlow probability to find the variance. Now, I believe we can find the standard deviation here. Reduce STD. Ah, what's happened here? TF math reduced STD. Does it not have an alias? What if we do tf.math.reduce STD? Must be either real or complex. So if we come here, input tensor. What's wrong with our tensor? Reduces input tensor along the given axis. Unless keep dims is true, the rank of the tensor is reduced by 1. Input tensor, the tensor to reduce, should have real or complex type. Does it have to be a float? This is a good little challenge. I'm glad I issued this exercise. We can work this out together. So where's our, here, dtype int 64. You know what I think this method might need? Is if we cast our E tensor as dtype tf int 32, this might work. Int 32. Input must be real or complex. Maybe float 32. There we go. Okay. So this is what I mean. Things may not be as they appear when you go through the TensorFlow library. So up here, we've got a few relatively easy methods compared to what we had to do here. But this has been a great practice as to how you might go about researching and trying things out to make something work. So if you ever get that error that we got just before, let's write this again. So tf math.reduce std e for our tensor. So type error. If you ever get the type error message, come to the documentation, which is what we did here. All right, so there's tf math reduce std. And check out the types that they're using in the example workflows. So see here, the reason why I picked up that we might need to change our tensor to data type float 32 is because they're using floats in their input sample here. So there we go. Returns the reduced tensor of the same D type as input tensor. Note for complex or complex 128 input, the return tensor will be of type float 32 or float 64 respectively. So usually, a lot of the time when you're working with TensorFlow, float 32 is generally sort of the standard type throughout the entire library. So if you need to change the type of your tensors, chances are it might have to be in float 32. But that was a good practice in exploration. Now in the next video, let's see how we're going to find the positional maximum and minimum. You might want to try this out now that you've had your expert problem-solving skills upgraded in this video. See how you might find the positional maximum and minimum of a tensor. I'll see you in the next video. So I was all ready for this video to jump straight into finding the positional maximum and minimum. However, after a little bit more exploration of the TensorFlow documentation, which can be a bit of a beast to tame, I found that we didn't actually have to jump through some of the hoops we did in the last video to find the variance. So look at this. I thought that we might just be able to go tf.reduce variance. It turns out we can find the variance of our tensor in a very similar way than what we've done here, finding the standard deviation, which is strange because with these methods, you can get rid of the math, but with the variance and standard deviation, you require the math. And so we've both learned something here. So I want to just show you here, if we want to go find the variance of our E tensor, we go tf math.reduce variance E, just exactly like we've done here in the documentation. And if you're ever stuck, you can just go through the documentation here, like tf.something, and just read up all the different methods. I mean, we're working with tf.math, so you might want to even try a fair few of these just to see what happens with what you're working on. But anyway, let's go back here. We'll find the variance. Input must be real or complex. How did we fix that? We go tf.cast. Let's change this D type to tf float 32. And, oh, we forgot a little bracket on the end. Wonderful. We get a very similar number up here to our variance that we found using the TensorFlow probability. So, turns out we actually don't need access to TensorFlow probability. However, what we just went through was a great exercise in figuring things out. I mean, at first you'll try something and it might not work, and then you'll find a fix to it. Then you'll find that, hey, the fix probably wasn't even the best way of doing it. We did a little bit more research and we found we wanted to find the variance without inputting any other libraries aside from TensorFlow. We can just do it like this. But anyway, let's get into finding the positional maximum and minimum. Now, when might this be helpful? Well, you're going to see this a lot when your neural network outputs prediction probabilities, which we haven't seen yet. But if we go here, so remember our little example where we got our images, we input it into some numerical encoding, goes through our neural network, finds the patterns in there, adjusts its random weights that it initializes with, it updates its representation outputs. And then here, oftentimes the representation outputs are referred to as prediction probabilities. So in this case, 983 is the highest number, 0.04, 0.013. So imagine if above here, if this column was, say, ramen, and this column was, say, spaghetti, and this column was, say, not ramen or spaghetti. So in this case, this number, the highest output, this is our ramen column, would be dedicated to ramen because the first index here, the 0th index, the highest number goes to ramen. And then if we wanted to turn this row into labels, we might go ramen, spaghetti, not ramen or spaghetti. Which one has the highest value? The index where spaghetti occurs. And then for this one, which is no food, so ramen, spaghetti, no food or spaghetti, this is the highest number. So we might want to get this index. So that's what I mean by finding the positional maximum minimum. At which index of the tensor or of this row does the maximum value occur? So in this row, it occurs at the 0th index. In this row, it occurs at the first index. And in this row, it occurs at the second index. But let's have a look how we might do that in code. So the first thing we're going to do is create a new tensor. So create a new tensor for finding positional minimum and maximum. We go here, f equals tf random. We'll create a random tensor with uniform this time. We'll give it a shape of, we'll get it 50 long. Let's have a look. Beautiful. Now I wonder if we go here, tf random set seed equals 42. Do we get the same numbers? So this one is, you help me remember what's this first number, 6645621. Okay, beautiful. So if you use random seed 42, you should get the same numbers as me. Don't worry too much if you don't, if something's changed between now and when you watch this video, but we just need a tensor with 50 random numbers and we can work with this. So if we wanted to find the maximum element position of f, meaning at which index does the maximum value occur? So I'm going to guess, let's have a quick look. There's 948. Can we beat that? Yes, we can. There's 967. So that'll be about, maybe 43. Let's try. TF. So find the positional maximum. Now, the positional maximum is often referred to as argmax. So I believe it's the same in NumPy, mp.argmax. If we wanted to find the docstring here, returns the indices of the maximum values along an axis. Same with argmax. Returns the index with the largest value across axes of a tensor. So let's do it. Let's put in our 42. Oh, so we were close. Now, if we were to index on our largest value position. So what I mean by this is if we grab our f tensor and then we find argmax f, what value are we going to get? Boom, it's that value there. And then if we go find the max value of f, tf dot reduce max f. Do all these values line up? Wonderful. So this should, now let's check for equality just to be safe. If we go argmax tf, argmax f, does this equal, we might put a little assert here, because this will error if they don't equal. No error. And then if we take away this assert, we should get true. Beautiful. So this is we're indexing. Does this make sense that they are equal? Because look, we found the positional maximum, which gives us position at index 42, which is this one. That's the maximum value of this tensor. And then we can index on our largest value position. So it's saying, hey, take the F tensor and grab position 42, or grab the value from position 42, which is this. Yes. Now, if we use just our reduce max method, which is saying, hey, find me the max value of F, we get this value, and then we check to see if they're equal. Beautiful. Now, another one you might use, I don't use this one as often, is finding the minimum. So wherever the positional minimum occurs in here, can we find it? There's 0.03, that's pretty low. So maybe it's that one. Or there's 0.009. So I'm guessing that might be at, let's go 21 or 20. So find the positional minimum. We want to do TF. You might be able to, if argmax finds the maximum, what do you think finds the minimum? If you guessed argmin, 100 points for you. Boom. So position 16, let's find out what it is. Find the minimum using the positional minimum index. So F, TF, argmin, F. 0.009. So that was actually 16. There we go. So that's index 16. Beautiful. Alrighty then. So what we might do in the next video is we can see how we can squeeze our tensor. In other words, removing all single dimensions. So have a go at this. Maybe create your own tensor. Can be as big as you like. And practice around using the argmax and argmin methods to see if you can find the minimum, maximum positional values of your tensor. And I'll see you in the next video. How'd you go? Did you create your own tensor? Did you find the minimum and maximum positions? I hope you did. But for now, we are on to the next part, which is squeezing a tensor. Oh, we're going to give our tensors a big hug. In other words, removing all single dimensions. You're going to fall in love with tensors by the end of this course if you haven't already. Now, what we might do is, as always, we need to create a tensor to get started. Now, I might go here, G. Are we up to G? Yeah. E, F, G, H, I, J, K, L, M, N, P. I won't do that again. No promises, but I like to sing. Now, if we go here, what have we got? So I'm creating a similar tensor to what we did before, random uniform, but in this time, we're going to use the shape parameter to add a few single dimensions right to the start. So if we check G, look at this. So we have just, actually, let me use our faithful random seed as 42. Beautiful, we're getting the same numbers there. Yep, 6645, 621. Maybe I'll know that off by heart by the end of this course. And so we have here, the shape is what we have to pay attention to with squeezing. So this is shape 1, 1, 1, 1, 50. So see here, we've got a few square brackets, 1, 2, 3, 4, and then the innermost square brackets is where the big dog 50 is sitting. Now, what we're going to do with squeezing, it's actually quite a fun little concept. So if we go G shape, we get that. Now, if we were to go G squeezed, that could be our TensorFlow wrapper name, G squeezed. TF squeeze, and now, actually, we'll check the docstring. Removes dimensions of size 1 from the shape of a tensor. Now, if I were to run this, what do you think G squeezed new shape is going to be? I'll give you 3, 2, 1 to guess, and now let's check. Boom. So there we go. So what squeeze does is, we just read that before with the docstring, but we'll read it again. Removes dimensions of size 1 from the shape of a tensor. So if your tensor has too many single dimensions and you want to just reduce it, So get rid of all these extra dimensions here and reduce it back to its essence. You can use the squeeze method. So that's a little tidbit there. Nice and quick video, this one. And the next one, we're going to cover one-hot encoding. So I'll see you there. Okay, so if you wanted to one-hot encoding tensors. Now, what is one-hot encoding? Let's check this out. What is one-hot encoding? If you've done any machine learning before, you might have come across one-hot encoding, but it's a very important concept in terms of preparing data. This is a great website, by the way, Machine Learning Mastery. So let's check what this says. There, okay. So this is a great example. We'll create our own in a minute, but let's just have a look here. So we've got 3 columns, red, green, blue. So row 2 has a 1 for red and 0 for the rest. So that is one-hot encoded for red. Row 3 has a 1 for green, but 0 for red and blue. So that is a one-hot encoding for green. And row 4 has a 0 for red, a 0 for green, and a 1 for blue. So that's a one-hot encode for blue. So that's a great way to turn, if we just remember, what do we have to do when we're passing our data to neural networks? We have to find a way to numerically encode it. One-hot encoding is a form of numerical encoding. So if we had the colors red, green, blue, and we wanted to pass it to our neural network, it would look at that and go, you know what? I'm very smart. I can find out patterns and numbers, but when you pass me words, red, green, blue, I can't understand them. So we could one-hot encode those words. Red could be 1 for red, 0 for blue, 0 for green, and so on, and then pass those as a tensor to our neural network. So let's have a look how we might do that in code. What we should do is create a list of indices. So values, pretend this is, let's get our sum list. Sum list can be 0, 1, 2, 3. In other words, maybe we go, could be red, green, blue, purple. And now, if we wanted to one-hot encode this, we can go one-hot encode our list of indices is tf.onehot sum list. We're missing one positional argument. All right, let's look up the docstring. What does this say? tf1hot returns a one-hot tensor. If on value is not provided, it will default to a value of 1 with type dtype. Okay, where's the example? Here we go. For example, indices equals that, depth equals 3. We need to pass a depth parameter. Okay, so the output's going to be 3 pi 3 because this is 3 long and the depth is 3. So let's figure this out. Depth. If we have 4 elements here, what I've kind of given it away here, so pretend you can't see that. Well, it's going to be 4. Let's try it out. There we go. So do you see what's happened here? What kind of tensor we've created? We've transformed this tensor, sum list, into one hot encoded version of itself. So for the first row, this relates to the first element. So it's got a 1, as you see, for where 0 occurs, but then 0 for all of the other values. And now for this one, we've got this refers to this value here. It's got 0, yes, and a 1 because this is a number 1 here, and then so on for the other 2 values for each rows. Beautiful. Now, a fun little thing that we can do is that if we wanted to change this from, you're rarely going to use this in practice, but I want to show you anyway because it's cool. If you wanted to get rid of, rather than using 1s and 0s, we can use on value and off value and pass them different values. So let's go specify custom values for one-hot encoding. If we want to do tf one-hot, sum list, depth can be 4, and then on value can be, I love deep learning. And then the off value can be, let's go, what could we do? I need something fun here. I also like to dance. Boom. Let's see what this comes out with. Oh, yo, I love deep learning. I also like to dance. 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 Yo, I love deep learning. I also like to dance. Did you know I like to dance? So have a practice with TF1 hot. Maybe create some of your own on values, off values. Again, rarely will you ever use them when you're passing them to a neural network, because a neural network, what does it love? It loves numbers. But yeah, this is just a little fun exercise to practice one hot encoding. Now, if we look up the tf.1hot, I believe it requires, so the indices, the indices have to be a tensor of indices. Okay, well, that makes sense. So yeah, go through the example there, create your own list of indices, and then one hot encode it, practice around, see what happens if you change the depth parameter, and then change the on value and the off value. And I'll see you in the next video. Did you have some fun creating one hot encoded tensors with different on and off values? I hope you did, and I hope you're loving deep learning. We actually haven't covered too much deep learning yet. We're still in the fundamentals, but I do believe you do like to dance. So by the end of this section, you're going to be able to dance through your way through TensorFlow code. And speaking of which, let's do a little bit more dancing through there are some math functions. I just want to show you how to use a few more of these that you may come across. There's a lot here, as you see, tf.math overview. We got a whole bunch here, but let's practice with a few more. We can never get enough practice. We might go a few common mathematical operations, a squaring, log, and square root. So let's see how we'll do that. First things first, let's create a new tensor. So this time we might go h, I believe we're up to. So tf, I'm going to show you a new way to create a tensor. 1 to 10. Nice and simple. Oh, let's see it. There we go. Now, if we want to square it, how do you think we might do it? TF square h. Beautiful. So we get just the square of all that. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, etc., etc. And then if we wanted to find the square root, let's find the square root. We come over here. Maybe we go square root. Will this show us? There we go. TF math square root. Beautiful. Let's try that. Now, I believe it may have an alias. We can just skip the math part. Oh, what do we got here? Invalid argument error. Value for attribute t of int32 is not on the list of allowed values. Okay, this is good. So again, we're coming across a value error where it's saying that int32 is that the type of our tensor. Yes, it is. Int32 is not in the list of allowed values for this function. So we want b float, half float, double, complex 64, complex 128. Okay, let's change it into a float. TF cast, and the d type is going to be TF float 32. Oh, forgot again. Boom! Look at that. There we go. Actually, let me put this one above here so that you'll know for future reference, is that this is going to be will error. Method requires non-int type. So if we put here just h, we get an error. Wonderful. How about we find the log? So we go here, find the log. Now, again, TensorFlow, oops. We want to go up here and search for log. TF math log, wonderful. Computes the natural logarithm of x element-wise. Has it got an alias? I'm pretty sure we can skip the math part, but if not, we can try it out. So find the log, TF log of h. Has no attribute log. Oh, do we need math for this one? We do. Oh, again, we get the same error as above. So what do we have to do here? Value for t of int32 is not on the list of allowed values. What do we have to do? I'll give you a hint. We have to turn it into a float, or at least one of the allowed values. We've got some rules here. So we go here, tf cast h dtype equals tf.float32. Will this work? Wonderful. There we go. So that's just an example again of how many different functions you're going to find in TensorFlow, and a little bit of practice again, as I can't stress this enough, is how much practice we're going to need sort of just making sure our tensors are in the right data type. So have a play around with some of the functions in tf.math and see how many of them, pick 3 and try them out, the ones that we haven't covered so far, and see if you come up against any errors like this, what you can do to fix them. So that's a little challenge before the next video. We've covered a whole bunch so far. We've even seen before how tensors can interact with NumPy arrays, but let's have a dedicated session on tensors and NumPy. So if you've done any numerical computing before or any type of data science or machine learning, you've probably used NumPy. So if we come here, what is NumPy? Not going to dig too much into this because we want to get focused on using it. But chances are, there we go, the fundamental package for scientific computing with Python. So NumPy is a fundamental library for any type of numerical computing with Python, and it's all built upon the NumPy array. So TensorFlow interacts beautifully with NumPy arrays. And we can see an example of that by, if we create a tensor, this is what we've seen before, directly from a NumPy array. So if TensorFlow is built upon the tensor, NumPy is built upon the array, and the beautiful thing is that they basically have full interoperability. I believe that's a word. That's like a fancy word for they work together quite nicely. So there we go. We create an array here, and then we pass it to tf.constant to turn it into a tf.tensor. Beautiful. And now we can convert it back from a tf tensor to a NumPy array. So convert our tensor back to a NumPy array by just going np array j, and then we can check the type here by going type np array j. There we go. So np array j turns it into a NumPy array, and then when we check the type, it turns into a numpy.nd array, which is NumPy's base type, just like TensorFlow's base type is tf.tensor. All right. And we can also do the same thing as the cell above by convert TensorJ to a NumPy array using, if we go j.numpy, we've also seen the NumPy method in Tensor before as well, .numpy, and then if we check the type, j.numpy, we go here. Beautiful. So we can convert it back to a NumPy array there. Now, where this might be helpful is sometimes if you have, say if we have, let's rewrite j to be tf constant, it's just a single number there. If we wanted to have access it just as the float on its own, we can actually do .numpy, and there we go, that'll give us access to it there. And if we want to go there, so the beautiful thing about being able to really easily convert our tensors to NumPy arrays and NumPy arrays into tensors is that if there's some sort of functionality that we want to use with that doesn't work with our data in tensor types, we can convert it to a NumPy array and use it there, and vice versa. So if we delete that, let's see, there's one more thing you should know, and that's default types of each slightly different. So if we want to create numpyj equals tf constant, we'll create this directly from a NumPy array, just as we've done before. It's going to go np array, same as above, 3, 7, 10. Wonderful. And then if we want to go tensorj equals just tf constant, we'll create this one directly from a Python list, 3, 7, 10. Now, if we want to go check the data types of each. Now, we've had some practice doing this, so you might be able to know if we wanted to check the data types of NumPy-J and TensorJ, what might we use? If you guessed we use the dtype attribute, you'd be 100% correct, TensorJ. And if you didn't guess correct, well, that's all right. We get to practice. Boom. So there we go. So if we create a tensor from a NumPy array, the default type is float64. Whereas if we create a tensor from a Python list or directly through TensorFlow, the default type is going to be float32. Now, the reason why this is important is because, remember, we actually had some errors up here where we had to change the type of our tensors from a certain data type to another data type. So this is where I want you to be aware is that if you do convert your NumPy arrays into tensors, they may have a different data type to compared to if you created your tensors directly from TensorFlow. So just be aware of that. One of the main issues you'll run into when computing with different tensors is different data type issues. So treat this as your heads up. But that's a quick reiteration of tensors and NumPy. Remember, NumPy is a fundamental package for scientific computing with Python, and chances are when you're doing machine learning and deep learning, you're going to run into NumPy somewhere. So keep in mind, TensorFlow works beautifully with NumPy arrays and vice versa. Welcome to neural network regression with TensorFlow. Now, we've seen some of the basics of TensorFlow in the previous section. Now we're going to get hands-on building some neural networks with TensorFlow, specifically neural networks for regression. Now, before we get into things, I'm going to start this lesson off with a slide called Where Can You Get Help? Now, this is very important because learning a new concept is challenging, of course. So, that being said, if you do get stuck, here are the steps I want you to take. First of all, follow along with the code. I'm going to be writing it with you. Remember our motto, if in doubt, run the code. If I'm going too fast, that's all right. Slow the video down, then try it for yourself. If I'm going too slow, you can speed the video up and beat me. If we're writing TensorFlow code, don't forget in Google Colab, you can press Shift Command Space to read the docstring. That will get you a little bit of information about any of the functions that we're running. And then, if you're still stuck there, if the docstring doesn't have that great of an explanation, remember, most docstrings in TensorFlow have examples of different code, so try it for yourself. But then, still stuck, search for it. You're going to become very familiar with these two resources here, Stack Overflow, and of course, the TensorFlow documentation, which is forever improving, forever getting better. So it's very vast, but with a lot of experience, hands-on practicing, checking it out, you'll start to get much more familiar with it. Then, once you've learned some things from searching for it, don't forget to try the code again. Remember, back to the motto, if in doubt, run the code. You can't break anything. And finally, if you're still stuck, ask a question. I'm going to emphasize here, including I'm putting inverted commas. You can't see my face in this video, but I'm doing the inverted commas symbol with my fingers. The dumb questions. Don't forget the Discord chat. Ask a question if you're stuck. Very important skill to have is asking the right question. Now, with that being said, if we're going to do neural network regression with TensorFlow, you might be thinking, what is a regression problem? So let's have a look at a couple of examples of what regression problems are. Here we go. Some example regression problems. Say we're trying to predict the house or the sale price of a house we're interested in. So how much will this house sell for? If we've got a house down the street and we want to try and predict how much it's going to sell for, we might ask ourselves, how much will this house sell for? We just said that, didn't we? Another regression type problem is, how many people will buy this app? Or how much will my health insurance be? Or how much should I save each week for fuel? Now you'll notice a trend here with these questions. It's how much or how many. That's one of the key points of a regression problem. It's predicting a number of some sort. And if you're thinking about in terms of price or numbers in these types of questions, well, there are other types of problems where a regression, well, we can turn them into a regression problem, such as trying to predict the coordinates of where the boxes should be in an object detection problem. So these are numbers here. So say we've got 1390, so that would be on the x-axis. This corner, the top left corner of this particular box here, should be at 13 pixels in, but 90 pixels down, and so on for the top right corner, the bottom right corner, and the bottom left corner. And then again, we could do the same with these corners here, the top left. Remember, this is the perpetrator who hit and run on my car. So if I was going to build an object detection model to look at security footage around my home to see if I can find the people who hit and run on my car, I might train an object detection model, specifically a neural network regression, to try and predict the corners of where the bounding box should be around my target object. So this is what I want you to start thinking about. Although we have a kind of a one-liner definition for regression problems, predicting a number, is that a lot of the time in machine learning and deep learning, how you sort of think about the problem will definitely define how you approach that problem. And again, if you're not satisfied with the definitions here, this is what we can do. So what is a regression problem? Regression analysis. Here we go. In statistical modeling, regression analysis is a set of statistical processes for estimating the relationship between a dependent variable, often called the outcome variable, or one or more independent variables, often called predictors, covariates, or features. Okay, so we want to predict the relationship. So say this line, that's the relationship there. So the dependent variable, in our example problem of trying to predict the house price, our dependent variable might be the price of the house. So the house price is the outcome we're trying to predict. And the independent variables, often called predictors, covariates, or features, might be the number of rooms in the house, or the number of bathrooms, or the number of garage spaces, or all three of those combined. So the independent variables, so we might have 10 different houses with 10 different numbers of bedrooms, 10 different numbers of bathrooms, and 10 different numbers of garages, and 10 different house prices. And we might want to build a model to take in all that information and then predict what the house price might be. So with that being said, we're going to get into more examples of this later on as we write code. But let's have a look at what we're going to cover. Broadly, of course, we're going to be writing lots of code to do these things. We're going to cover the architecture of a neural network regression model, so specifically the building blocks of a neural network regression model, the input shapes and output shapes of a regression model, in other words, the features and labels, or, in Wikipedia terms, the dependent variables and the independent variables. We're going to look at how we can create custom data to view and fit. We're going to take care of the steps in modeling, such as creating a model, compiling a model, fitting a model, and evaluating a model. If all of these don't make sense right now, don't worry. We're going to get very hands-on with them and they'll start to make sense as we code them. We're going to look at different evaluation methods for regression models. And finally, we're going to look at how we can save and load our models so that if we do train a machine learning model and we save it, we don't have to go through that process of retraining. And if we want to load it into our applications going forward, we can do that using our save and load methods. And finally, how are we going to do this? A big emphasis between the chef and the chemist. Chemist is very exact, whereas what's a cook do? A cook tries things out. A cook experiments, pours in little bits of different flavoring. We're going to be cooking up lots of code. So with that being said, here's what we're going to cover. In the next video, let's have a look at what the inputs and outputs of a regression problem or neural network might look like. So if we're dealing with regression problems, well, we're trying to build neural networks to solve regression problems, what might be our inputs and outputs? Remember, in machine learning and deep learning, a lot of the time your focus will be on defining your inputs of your algorithm and what the outputs of your algorithm look like. So let's say we wanted to predict the sale price of this house. Now, this is an actual house that was up the road from me, not far from where I live, that was up for sale. And say I wanted to build a machine learning model to try and predict what I should offer if I was going to auction what this house should sell for. So again, here's our little diagram of what we're going to be focused on. We have the inputs. So what might our inputs be if we're trying to predict what our house might sell for? And what might the outputs be? So if we're just looking at this diagram, and if we want to build a machine learning algorithm, we might have to build this ourselves. But first, let's focus on the inputs and outputs.